Hello everyone and welcome back. Now, keeping with the trend of the previous video where I introduced the computational method of Newton's method, I would like to consider another computational method in solving optimization problems. And what we're going to discuss today is linear programming. Now, I am going to focus on a very specific, very simple aspect of linear programming to get the general idea across. But I would like to emphasize that linear programming is a widely used method in optimization problems that can be quickly and efficiently solved on the computer using what are called simplex methods. Now, I'm going to focus everything today on the graphical way of solving these optimization problems that come into play with linear programming. Okay, so this is just going to be a small aspect. Of course, it's going to be limited because we're able to draw all of the solutions. Typically, linear programming routines deal with very high numbers of variables, and they can be implemented on computational software such as MATLAB, Python, whatever your favorite is, but you can also do them in something like Excel, right? So they don't require a whole lot of programming expertise in order to implement these algorithms. Okay, so let me show you the basics of what I want to talk about. And I want to do this in an example-driven way today. Let me ask you the following, okay? If I'm gonna give you, say, a function, I'll call it p, and it's going to be 40x plus 30y. And I would like to optimize this. All right, so maybe maximize, maybe minimize, optimize in some way. We can do sort of both of them at the same time here. So I'll show you how this works. And I want it to be subject to, well, I'm going to give it three constraints. So 3x plus 2y is less than or equal to 24. Then x plus 2y is less than or equal to 16, and x plus y is less than or equal to 9. Okay, so I have three constraints. I have one function I would like to optimize. Now, before we go any further, I want you to notice something about all of my constraints and the function. They're all linear. Okay, so this is where the linear part of linear programming comes into play. This is only going to be applicable to both optimization problems and their constraints being linear. This is not going to work in general for nonlinear functions, right? Nonlinear functions are a whole class of really, really complicated problems where we need things like maybe Newton's method to help us. In this case, everything I'm going to talk about today is going to be in this linear regime. The last piece of this, of course, is we're going to need x and y greater than or equal to 0 as well, right? So I'm not going to give you a specific motivation for this. I just want to deal with an abstract example to start with, okay? Everything is linear. Let's sketch it out. So let's sketch out the feasible region, okay? So first of all, it's in the top quadrant. That's my first constraint right here. Then I've got one function. So let's make it like this. This point goes through the point 8, 0. And this is the function 3x plus 2y equal to 24. So that is exactly this equality condition right here. Then I will have another function which goes through the point 0, 8, which maybe looks something like this. And this function is going to be x plus 2y is equal to 16. And then I'm going to have one more condition, x plus y is equal to 9. Let's put it maybe right here. Okay, so not the best drawings that I've ever done, but I think you get the point. And I'm going to label these intersection points as well. So you can solve for all of these intersection points, right? You know how to work with equations of lines. And in this case, this is 6, 3. And the upper one is 2, 7. So again, not drawn perfectly to scale. But what I want you to notice is, what is the feasible region? Well, the feasible region is above the x-axis, to the right of the y-axis, underneath this line, so that's underneath the line right here, underneath this line, that's underneath here, and underneath this line, which is underneath here. So the feasible region is this simplex that is bounded by all of these lines. That checkered region, and it includes up to the lines. Now, I'm not going to go into the mathematical proof of this, but this is what's called a convex region. And what we know for these linear programming problems is that the optimum value, both maximums and minimums, are at exactly these labeled so-called corner points, right? So all of these points of intersection that I have, these are called the corners. And what I know about linear programming problems is that the optimum values are always at the corners. Now, why is this good for me? No Lagrange multipliers, nothing complicated. I just need to check 1, 2, 3, 4, 5 points. See what is going to be the optimum. Okay, so let me actually do it. Let's just check the corners. Let's do xy equal to 0, 0. Well, when I put this into my function p, again, this is what I wanted to optimize, this gives me p is equal to 0. That's easy, right? X and y are equal to 0. Okay, then let's do xy equal to 0, 8. Okay, so that's this point up here. When I put this into my function, x is equal to 0, y is equal to 8. This gives me 240. All right, let's keep going. X and y is equal to 2, 7. So we're going to go counterclockwise around this little simplex. In this case, my p is 330. Okay, let's do another one. X and y is equal to 6, 3. P in this case is, this is 330, pardon me, and this should be 290. And then, at the final point, 80, I've got 320. So now, I've got a table of values, right? Nothing fancy anymore. All I need to do is just check which one gives, say, the maximum and which one gives the minimum. Well, right here is the maximum. So if you asked me to find the maximum of that function over that feasible region, it is going to be 330. And it's at the corner point, 6, 3. Similarly, if you asked me to find the minimum, it's at the origin. X is equal to 0. Depends on how the problem was asked to you, right? I just said to optimize it, so we're going to do both at once. But I want you to see that both of those things happen at the corners of this thing. Okay? That's the beauty, is that we can do this graphically, and we know that the optimal solution is at the corners. Now, one thing that you might be wondering is, you might be saying, Jason, I've seen you draw a picture like this before. We did this for the TV example when we had to use Lagrange multipliers. And if I remember correctly, the solution was not at one of the corners. Why not? Well, I urge you to go back and look at that example. Yes, my constraints were linear. Remember, I had s plus t is equal to 10,000. But what was not linear in that example? The thing you needed to optimize. Okay? So the profit function in that case was nonlinear. So none of this works. The only place where this linear programming works is when everything involved is linear. In that case, I got a shortcut. I just checked the corner points. Nothing too fancy. All right, let's put this in a modeling framework, okay? So let's actually do a math model of this thing. Now, I have a very complicated word problem that we can walk through in order to understand this thing, okay? So let me read it out loud. And basically, here's the basic idea. You are a pet food company, and you make two kinds of dog food, okay? I'm going to call one Meaties. I'm going to call one Yummies. Now, each package of Meaties has 2 pounds of cereal and 3 pounds of meat, while each Yummies has 3 pounds of cereal and 1.5 pounds of meat, okay? So it's cereal and meat. That's the only two things that we're interested in here. Then, my pet food company believes that I can sell as much dog food as I could possibly make. So there's no restrictions on anything here, okay? All I need is that the number that I make is non-zero. And Meaties is going to sell for $2.80 per package, while Yummies is selling for $2 a package. Now, I'll put all this down in a moment, okay? Now, the dog food company is limited in several ways. First of all, my company can only buy 400,000 pounds of cereal each month, and that cereal costs me 20 cents a pound. Now, I can also only buy 300,000 pounds of meat per month, and that costs me 50 cents a pound. Okay, also, my factory that I use to make this dog food, it requires that I can only make 90,000 packages of Meaties a month. Something about this machine, okay? Let's not think too heavily on it. All right. Now, the cost of blending and packaging the dog food is 25 cents per package for doing Meaties and 20 cents a package for doing Yummies. All right. So, how much of each package of dog food should I make to maximize profit for my dog food company? Maybe I'm a manager there and I want to get a raise. How should I do this? Well, okay, so there's a lot of moving parts in here. First of all, let's let M equal to the packages of Meaties produced each month. We're doing this on a month-to-month basis. And then let's let Y be the packages of Yummies produced each month, okay? So same basic idea. Okay, so again, we're in the position of maximizing profit, and we all know profit is revenue minus cost. Okay, so then let's figure out some components here, okay? So for Meaties, the cost per package here. All right, I sell it for $2.80 per one package. But cereal costs me 20 cents a pound, and I have 2 pounds of cereal in there, okay? So from the $2.80, I'm subtracting 40 cents for the cereal. Let's say cereal underneath it. Similarly, I have 3 pounds of meat at 50 cents. So this is meat. And to blend this thing, it cost me 25 cents right off the bat, blending and packaging. So that means on a single package of Meaties, I can make 65 cents. Now, I can do the same computation for Yummies. And in this case, Yummies is going to yield a 45 cent per package, or 45 cents per package profit. So therefore, my profit is going to be, let's call it P of M comma Y. This is going to be 65 cents per Meaties package plus 45 cents per Yummies package. It's linear, right? So it's fitting into the framework that I started with. That's pretty simple so far, right? 65 cents for every package of Meaties that I sell, 45 cents for every package of Yummies that I sell. All right, so my goal is to maximize this profit. But let's see what it's subject to. Subject to, well, what do I have? Well, the first thing is the cereal constraint. Now, 2 pounds of cereal per package in the Meaties, plus 3 pounds of cereal per package in the Yummies, and the number of pounds of cereal I could possibly have every single month is 400,000. Okay, so this is the cereal constraint. Same thing, I can do a meat constraint. 3 pounds of meat in the Meaties plus 1.5 pounds of meat in the Yummies, and I can only have 300,000 pounds of meat per month. So that's my meat constraint. Similarly, I have this weird constraint on my machinery that says I can only have 90,000 packages of Meaties produced, right? So this is the Meaties machine constraint. And of course, M and Y have to be greater than or equal to 0, or else this wouldn't make sense, right? Imagine giving me an answer saying you should produce negative 20 bags of Yummies a month. That doesn't make any sense. So what this provides me with is an optimization problem. It's actually a linear program. And in fact, you can graph this out. The feasible region looks a lot like this. It's basically the same sort of structure. Let me sort of sketch it out. In this case, I have M here, I have Y here, and I'm going to just sort of roughly sketch out my feasible region. This is my feasible region. All that I'm doing is bounding it by the various constraints. Okay, so in the top quadrant, this vertical line here, that's the M equal to 90,000 constraint. And then these two lines, that's these lines, the meat and cereal constraints. And so, basically, you can find all 3 corner points here. Okay, so let me enumerate them. So my corner points. Again, this is the beauty of linear programming, especially when you only have 2 independent variables. The solution is at the corner points, and I can graph this out. So all I need to do is just figure out what the corner points are, right? The math modeling part of this, okay, I put together a model. That's wonderful. I figured out what I needed to do. I figured out what my restraints are. I figured out what my feasible region is. And then really, it's just finding a bunch of corner points. One is at the origin. Another one of them is right here, 90,000. Comma 0. That's if you just maximize production of the Meaties and don't produce any Yummies. Okay. Another one of them is going to be at up here. So that's going to be 0, no Meaties, and Yummies produced to the maximum here. So it's going to be given by these lines. And in this case, it is 133,333. Okay, so it's kind of an ugly number. Then another one is 90,000. So it's this point right here, comma 20,000. And then my last corner point is this one right here, 50,000. And then comma 100,000. Okay, so in this case, I've got all 4 corner points, right? So if this is number 1, that's right here. Number 2, that's this guy right here. Number 3 is right here. number 4 is right here, and number 5 is right here. All that you need to do is take these 5 pairs and put them into my function right here. And just say which one gives the biggest number. Well, turns out that the maximizer is when the meaties production is 50,000 and the yummies production is 100,000. So it's this 5th point, and the profit in this case, well, your profit is $77,500 per month. Remember, this is being done on a monthly basis. Now, which one of those points was this? It's this one right here. This is the maximizer. That's it. That's all you have to do. That's the beauty of linear programming. Okay, so as you can imagine, as things go into higher dimensions, if you have more independent variables, then things become much more complex. But the beauty of this, again, is that we have numerical procedures, computational methods that we can hand this off to, and they can take care of our homework for us. Okay, I'll see you in the next video, everyone.